a middle mass particle when it was discovered, so it was called a meson. Anything ON just means particle of some kind. It's a middle-sized particle, meson. Right? So some mesons, there's a whole family of them now, have spin 1. Okay? Integer spin. Interesting. Okay? Now, interestingly, the particles that have integer spin, like 1, 2, the graviton, the hypothetical quantized particle that's responsible for the interaction of the gravitational field, the graviton, the particle of gravity, has spin 2. Okay? So it's known those particles that have integer spin, they do not obey the Pauli exclusion principle, and those that have half integer spin do. Now remember earlier on, quite a few lectures back, Pauli exclusion principle says you cannot have two quantum particles in the same state, okay? Because well, then the multi-particle wave function goes to 0. The terms cancel out. Right? We did that quite a few lectures ago. Okay, so I'll say that again. Half integer spin particles do obey the Pauli exclusion principle. You can't put two of them together, so to speak. And those that have integer spin do not obey the Pauli exclusion principle. So you can put as many as you like together in the same state, right? So they behave very differently. The half integer spin particles are very seclusive. They don't like being with others. You can have two of them together, but at least one of their quantum properties has to be different, and that is the spin. So, for example, in an atom, you can have, like in the inner layer, you have two electrons, and so they have all the quantum numbers are the same. They share the same quantum numbers except for one, and that's the spin. One of them will have spin up, the other one will have spin down. But I'm getting a bit ahead of myself. Okay? Now, they have these two groups of particles, the half integral spin. They are called fermions, after the Italian-American nuclear physicist Fermi. It's the same Fermi of the famous Fermi paradox, like if intelligent life in the universe is commonplace, then where are they? That was Fermi's famous question, the Fermi paradox. So that Fermi. So fermions. And the other kind of particles with integer spin, they're called bosons. That's after the Indian theoretical physicist Bose, B-O-S-E, who wrote to Einstein, and the two collaborated and came out with BoseEinstein statistics, which is, don't worry about it too much, but it's a kind of statistics within quantum mechanics. There are two kinds. And the other one, interestingly, is Fermi-Dirac, so the same Fermi. Another genius. Well, they're all genii. So Fermi-Dirac statistics and Bose-Einstein statistics. So I guess at some stage I'm going to have to do quantum statistical mechanics at some stage. Alright, so bosons and fermions. Okay, so fermions do obey the Pauli exclusion principle, and bosons don't. So you can crowd as many as you like bosons, boson particles, together, so long as the temperature is low enough. And in fact, late 90s, that was actually done for having zillions of atoms that were bosons. They condensed, and zillions of them, into the same one state. The same, so they condensed, because they're very cold, to that state, and that phenomenon is labelled a Beck, a BEC, a Bose-Einstein. In other words, does not obey the exclusion principle, so you can put many particles in the same state, quantum state. Condensate, Bose-Einstein condensate, BEC, BEC, with all kinds of wonderful technological possibilities for the future, maybe quantum computing, and you can all sorts. The experimental physicists are having a field day right now, just exploring the things they can do with these BECs. All right. Okay. Now, before I get into the next topic, it's getting to be quite a long session on spin eigenvectors. I said I'd mention a bit about some of the text. Now, I was talking a bit about Gell-Mann, and one of the courses I will be talking about will be I'll be giving quite a few courses on Lie, that's L-I-E. Lie, Sophus Lie, was Norwegian mathematician, pure mathematician. And he's considered the father of infinite groups of Lie. In fact, those kinds of groups are labelled after him, Lie groups. And from the Lie groups you get Lie algebras, and Lie theory is Lie algebras and Lie groups, plus a bit of other stuff. So Gell-Mann took Lie groups, a particular kind of Lie group called SU3, which is special unitary in 3 dimensions. It's a 3x3 matrix representation of the elements of a Lie group, and the Lie group is SU3. There are representations of the elements of all kinds of different sizes, and there's a whole theory explaining the dimensions of these matrix representations. And he found he could classify the elementary particles by using different representations of these SU3 groups. Now all that's absolutely fascinating stuff. Why on earth are the elementary particles classifiable according to some abstruse branch of mathematics using Lie theory and representation of Lie groups? Right? Was the universe created? Was it designed by some hyper-intelligent, godlike mathematician? A deity? I think I've mentioned before in other lectures, but I'm increasingly open to deism. Traditional theism I find ridiculous. No theist at all in that sense. I find traditional ideas of religion just ridiculous, utterly incompatible with modern scientific knowledge. But deism, that to me is another story entirely. There are all these clues from science itself, like why on earth should the elementary particles be classifiable due to the representations of Lie groups? Where'd that come from, right? I mean, deeply mysterious and fascinating. Anyway, so all the math, the Lie theory and the particle physics you'll get in this course. It's well, you can just see it's just called quantum mechanics, but it's a bit deceptive. What I'm really interested in is the symmetries, and this book is about Lie theory and a bit of particle physics and classifying the particles using Lie theory, and it's 350 pages, and this will be an M1 level text. So I hope you will join me, because this course promises to be absolutely fascinating. In some ways I feel a bit sorry for most people. It's just the way the world is, but most people just don't have the intelligence to be able to get into this wonderful stuff, and therefore they remain ignorant of this absolutely jaw-dropping realization the way the world is, I mean, we're constructed from elementary particles, right? Well, except for that embarrassing little two clouds on the horizon, dark matter and dark energy, which actually comprises about 96% of the energy that we know of. We have no clue what dark energy is, and we only have suggestions. There's no real theory, no real hard fact yet on what dark matter is. But anyway, of the 4% that's left over, those elementary particles are classifiable according to Lie theory. And why is that? Fascinating question. Now, as another aside, the author of this text, this guy Greiner, a German physicist, still alive, I think. Now, he's famous in Germany because of his series of textbooks that he's written. He has educated a whole generation of young German theoretical physicists who've used his texts. And lately, the last decade or so, they've been translated into English. And I'm a great. I love Greiner. I love his texts, and I've got five of them here, and I'll give a course on each one of them as part of the MPC, the deGarisMPC series. So here's the first one. It's an M1 level course. So I'll give two more, also at M1.